afternoon, people. Thank you for joining. I'm pleased to introduce Eswar and Chaitanya here. They're going to have a talk about Codebase data and the Haskell Codebases. And over to you.
Hi, I'm Chaitanya. I'm working in JustPay. We are both software developers from JustPay. He's Eswar. I've been working in JustPay for about like 5 years, and he's working here for about 3 years. So about JustPay is like fintech, and we are having more than 500 Haskell developers here. And since it's a payment a fintech company, uh, the paths that we like chose are like all of our modules are like very critical, and that's where when we thought to like explore about code as data. So all our programming, all our like repositories and everything, our main programming language is Haskell, and we'll see more on how we used Haskell and how we used code as data in Haskell, and what are the tools we build on top of it, and how much of help it did in our process.
So today we are excited to share about our work our work in Code as Data. So there are a lot of tools that we built, a lot of on top customizations that we did on our compilers and all to basically help us to achieve this. A huge shout out to the GHC team, those who has written that Haskell compiler. It's really awesome. Yeah. So let's start with what is Code as Data. So before we deep dive in, there is a fundamental question that you can ask: what exactly is code as data? Maybe Chaitanya can answer it. Yeah.
So for example, see, take it any scenarios, take it any use case that we want to solve. The ultimate truth that we have is like code, right? We can have logs, we can have that, we can have this, but ultimate truth we have is code, right? So whenever some issue pops up or whenever whatever happens, we always wanted to query code. So if because that is what it boiled down to. We always if we want to know the anything, we have to like query code. So when we wanted to make this code querying like more easily, not just for devs, we want like anyone who is like working, anyone can query, who's like non-tech person also. We want to like help them to get their answers from the code without actually like going through all lines of code, because we have like big repositories and it's million lines of code. It'll be hard to go through everything. So we wanted to structure it properly. So yes, we can query code, but if it's not like if it's raw code, right, it'll be like still hard to query. So we always wanted to convert this code, whatever we have, into a structure and on multiple levels of information that we want. So so different use cases will need different kinds of information. So we always transform our code into a structured data set such that we can query on it for our multiple use cases, which we'll be like explaining in this demo.
Yeah. So simply at its core, it means that we want to treat code as some structured data set which can be analyzed, manipulated, and transformed. This isn't just about reading code. Like, let's say if I want to read code, I'll just go function. Oh, this function is calling this. So let's see what it's doing. It's more about getting a bit more deeper level of understanding of what exactly it does. So you can ask us why we reached to this particular paradigm kind of thing, code as data. So we had Vimal as the founder and CEO, who always like pushes us to limits. Like he has this very good thought process. So that's when he introduced us to this thing called code as data. He said, "Oh, can't we treat code as data?" Like I was like, "Okay, code as data." Like
Yeah.
it's not like PB data; it's like data. Okay, what can we do on data? So okay, then we started. Okay, if you want to treat code as data, what are the observations that we need to make? Chaitanya, can you just tell them what are the observations?
So, for example, see all codes, right? We are using Haskell and it's functional programming. So everything, right? We have like a patterns in our code. Whatever we see, Haskell itself is expressive. So we can see all patterns in our code, and then see whatever we build, right? We also wanted to scale across. And when we thought, right, if we are following some manual methods, for example, just someone can ask us like, in this feature, how many DB calls are there? Something like that. They can just ask us, right? For us to like manually go and check, and it can iterate over the time, and we cannot just it will be hard for it's not like we cannot give an answer, but it will be like time taking, and it will take its own amount of time to do that, right? But when we have tools like this where we can collect the data from the compiler itself, because we add our code into that using plugins or something, if we add like that, and it is like very easy for us to query. And this was possible because the code has like patterns, and when we think about scaling, this approach was like very much useful. uh, Coming on, like, if you ask us what motivated us to do, obviously, like Vimal always used to say is like, treat code as data. Like, whatever your answers you're asking for isn't available in the code, how can you make it easy for others, and all those things. So that is like very fascinating journey in JustPay. For example, we didn't start our code base right away with Haskell. So we had our code base in multiple languages like PureScript, ReScript, R, Julia, all those things. So, and mainly most of our code base was in PureScript, and the domain, like core logic of payments and everything. So that's like million lines of code, like more than 2000 modules. And we wanted to convert to Haskell. And then on this process, right, we cannot pause any development, or we cannot pause any releases or anything, because payments is evolving and we have to like continue to give it support. Just for migrating this, we cannot pause any integrations or nothing. We cannot pause anything. And because of that, when we do this, right, and we also wanted to do it, so there was a transpiler team who did that, and we were also happy to contribute to that. And when we saw, right, they converted this all PureScript code into Haskell using that transpiler, and which was like mostly revolving around ASDs. Then it actually, like, we also got much interested in knowing about this ASD, because it was like magic for us, because it transpiled and everything started working, and there was no issues, and it was like working very fine. And we were like, it's a great magic, and we also become more interested towards it.
So from this particular migration that we did, we didn't pause any current feature implementation, or let's say new feature or new gateway integration that we did. It is more or less like it was kind of seamless for us. So that basically brought us a lot of valuable insights. Along with those insights, we were more or less like, okay, what else can we do? Then I and Chaitanya started going into Haskell's real ecosystem. Then we were like, okay, what exactly can we do with Haskell? What are the boundaries that we can push?
And then, like, we also, when we migrated, right, after that also, we got a lot of refactorings. For example, we build our own frameworks inside, and we have multiple repositories. We want it to be adaptable and consider GHC upgrade or any library upgrade, all those things, right? All those things are considered, like, we wanted to do those refactorings. Yeah, we can do it traditional using manual efforts, but since our repos are big, and we wanted to like invest more time on doing things automatically, and that's when we come across like good tools. For example, we tried retry, which is good, but we were not able to use the type specifications of it. Then we come across like an amazing tool called Haskell tools in the community, but it was though using an old version of GHC. We adapted it to 8 and 7, and then we made a few refactorings in that as well. Using that, we all those manual refactorings, right, were avoided, and all features, like all these refactorings which is needed, adaptation of frameworks that we have, all those refactorings were done automatically using these tools. There is like a lot of refactorings that we have wrote on these tools, which is like we'll be sharing the repository links and all. Yeah, it's available. So that is when we were like very interested on these things, and then we thought like, yeah, this is some external tool that we have to
Let's tell them why we wanted to do those refactorings also.
Yeah,
Sure.
sure.
So it is more or less like because once we moved from PureScript to Haskell, we wanted developers to immediately get in hands, and then don't feel like, oh, it's a different language, you have tried it differently. So we had to add that added layer where it says where it feels like, oh yeah, we're just using the same language again, same functionality, same features. But internally, it is different on how you compile, how it gets compiled and all. We wanted to abstract it out from our current developers, like for them to easy transition. So we added some layer on top of it, which they've added some layer, and we wanted to remove that layer.
Yeah.
Yeah.
So when we wanted to remove that layer and use core Haskell, then we use these refactorings to remove all those things. That is what. And apart from refactorings, right? Again, coming to code as data, right? When we were thinking like, okay, refactorings are possible, but what more information can we take from code? That's what like we started like exploring GHC, and we found this amazing option called compiler plugins, where
So yeah, compiler plugins. What exactly are compiler plugins is in compiler we have multiple stages that that our code basically goes through. From each phase to different phase, it enriches with more information. So what Haskell provided us with is, you can plug in some code. It will run with that particular compilation's output, that particular compilation stage's output. And what we thought is, okay, we saw an opportunity where we can either tweak code or let's say transform it or even collect it out, like traverse the AST and all. So that's when things started a bit interested for us. So there are a couple of problems that we thought, okay, we can address it with very simple use cases, and folks around those are working in Haskell community and who has Haskell code base and all can reuse this kind of concepts that we are saying here. One particular thing is change versus effect. So we have when we have so many libraries that we work with, right? And we also have a lot of folks of Git repositories that we feel like, oh, let's tweak it, let's improve it and all. But how do we say this particular function, if we change, it's going to affect these all flows, right? So for that, what we did was we wanted to figure out a way where you say, oh, I make this change, and these are all the effects that it's going to cause. We want this before we went into QA testing. We want it statically. So we can also give it to developers itself, right, Chaitanya? So it will be more or less like, I'll just make a change. I'll just run it, and then it'll give me, oh, all these things you have to test. All these things might break. Isn't it interesting?
yeah.
And let's see how we did it. Yeah. So yeah. Okay.
So for example, we wrote a plugin which is like fdep. So what it ideally does is it builds a function dependency graph. So this plugin runs right after type checker. So what it does is for every function, right, it will go through like what are the dependent functions. Like that we have like a big function dependency graph as an output, so that whenever someone touches or modifies one function, he will know, okay, all these features are going to get affected, all these flows are going to get affected because of that. So that is how we started that.
So this fdep is actually there in our GitHub of JustPay.
Yeah.
We called something called Spider. In that repository, we'll have all the plugins that we're gonna write. You can visit it. We'll share links at the end. You can visit it. So GHC plugin, this fdep is basically a type checker plugin which runs on type checker AST. We traverse the AST, collect types, and then build graph. And that graph, we used it in so many places. We'll show you those places as well where we have used it.
Yeah.
But yeah, this is one which we say, okay, this function is going to, when we change the function, it'll affect. But let's say when it's across microservices or across repositories which don't do a function call, maybe an API call or a WebSocket or some other kind of communication that they do. The way that we communicate are with types, right? So for that, we wrote a different plugin, which basically what it does is it takes types and then it will basically map with functions. It will say in this function, these are all the fields from these types that are used. So with this, what happens is, let's say we have a common type in somewhere and then we use it in same server and then client. Then we will be able to say, oh, if we change this type in server or let's say in client, there should be equivalent changes here and there. And what all functions also that we're using. So we have a lot of common repos, which are like scaled out to different microservice repositories, which are more or less like, it'll say, oh, if you change this type, you need to change in all these places. So Chaitanya, can you explain how we build this tool?
So for example, like, CADA.
No, this is self.
Yeah. So this is also like, for example, consider we change a type in one repo, and since if we are importing it as a library or something, even the compiler will itself tell us, okay, this field has to be changed or something like that. But when we are running, like making it as like a microservice and multiple repositories are doing that, we have to like communicate in such a way that this change has been done and this is going to be deployed or something, so that the necessary services should also have the proper update, otherwise it will break. So this is like a central tool which will guide among other repositories also, such that this change, if you're taking forward, this has to be done other places also, else we are like flagging it or something, so that there is no possibilities of some runtime or issues that can occur ever between the internal system communication due to types.
So we'll tell you where this field inspector would be running. This is a group of plugins which basically runs at different stages. We collect some data from parser, some from type checker, some from core, and then we aggregate it to give us the type dependency graph, and then which also enables us to build that function-wise fields usage. See, getting all these details is really nice, but there is another tool which is quite exciting for us. Chaitanya, can you explain that?
Yeah, so this is CADA, which is code analysis and diff analysis. So ideally, like you can also think we can just do git diff and get the data, right? Yeah, we can get the data, but if we want to know which feature is affected, which flow it affected, it becomes hard, right? So in that perspective, when we did with AST diff, whenever there is a feature or whenever there is a release or something, whenever there is a PR getting merged, we always do this diff analysis. And after that, we interrelate this tool with the previous tools that we were talking about, which is like fdep and which is fieldInspector. We interrelate this output with that. So consider in this using that ASD, we get the list of functions that is modified, and based on that, we take the data from the function dependency graph, and we'll know, okay, all of these flows has to be regressively tested, all of these features has to be regressively tested, such that we are giving more confidence to the developer and testing. Obviously, it will be tested in traditional methods and it will be gone also, but then we are giving more confidence, such that this will help you in more yeah, it'll gain confidence. And one more thing is, for example, like consider even after a release or something, there is some issue or something came, we do RCs, we do check, right? That check also can be easier, because consider in you had something and you some DB function is causing some issue, you know exactly where that is in this path, right, using this analysis. And so that you can like just check that particular feature or that particular flow. For that, you don't have to like have a dev, or you don't have to like exactly go through all these codes. Your vision, like where you want to actually look, right, it'll be like very narrowed down, and it decreased like lot of amount of time for everyone.
In simple terms, for every PR that we raise, we'll be able to know what is the change, what is the effect. And along with this, just a nudge. So CADA is a diff analysis tool. It's built on top of Haskell tools. So do check it out. So what it does, it'll take 2 commits. You have to give it 2 commits and the git URL. It will clone it. It'll take first commit AST and it'll take second commit AST. And then it'll do a diff and then it'll give you a diff output, which you can then plug and play in a lot of places. It's up to your imagination. See, this is fine. This is like more or less like analysis that we can do. Now let's see how functionality would be helping us. I mean, how Code's data would help us with functionality as well. So we have something called symbolic code traversal. We have 2 things which is kind of static symbolic and then dynamic symbolic. In static symbolic, you don't pass, you'll just know what the path is. In dynamic, you'll have data which you can traverse through without executing a function, or let's say a flow. So in simple terms, symbolic code traversal, you can understand it is more or less like a GPS system for your code. You don't read code by line, it will just map out all possible paths that you can traverse. So even during when you're reading any function or anything, right, you would take, so it's basically dry running it. In other terms, it will give you what all possible dry runs that you can run. So you have to think, right, oh, in if all these conditions can happen, or in this case statement, these are all things that I have to handle. But let's say it automatically gives you all those possible paths that you can take during execution. So it is not like during execution, you get it before execution. So you'll get all the paths before even you try to run it. So in order to do it, how we did it is, yeah, I think this is fine. So, yeah. So so in Haskell, there is a language. I mean, there is an interpretation of AST which is called System FC, which is basically an adaptation on top of System F. What it does is it basically has very small AST, So whatever syntactic sugar that you're seeing when you're writing, right? Dot operator, or let's say lenses, or in any syntactic that you're given, it's all stripped out. It is basically everything is a function call here. It'll be very nested, but it'll have a very small structure. You'll have like app, case, let, only those you might be having. So it became very flexible for us to cover a lot of patterns to extract this particular symbolic traversal path that we are talking about right now. So we built a plugin called Course into Chart, which basically takes that core AST and then gives us a chart. Chart is basically a list of paths uh, in which your function might execute, or yeah, execute or terminate, whatever, success, failure, but it's a path. Ideally, it's a path. So this is also a plugin which runs at Haskell core, which runs on top of Haskell core. We get enriched information like since it's nested, it'll be a bit complex to work with, but it's really powerful. So it basically helps us identify unreachable code paths, understand complex control flows, and we can also verify behavior without actually even executing the function. So this is all like kind of static stuff. So you'll be able to also write out all test cases and all. And we can also find potential runtime issues even before they occur. Sounds interesting, right? So see, all analysis part, figuring it out is really good. Now, let's say when companies scale, they tend to hire, and also not only tend to hire, their core base also would increase dramatically,
Yeah.
maybe exponentially as well, right?
One point I wanted to tell on course in chart, that is that, see, for example, see, we used this also in identifying like whether we covered all test coverage. So it helped us increase our test coverage. See, because since our code base is growing and everything, there can be new case matches, or there can be new flows that can be added in a function, right? And we have to like make sure those cases are also added in our test cases. So for us to like do it like, yeah, the devs will report and they will add it to their test suites, or all that is fine, but we wanted to have like more confidence on that as well. So this, using this tool, right, we identified if we were able to not if any of the paths that can occur is not covered in the test case, if so, we go and add it in the test case. So it's a loop, and it keeps identifying it, and this helped us increase our test coverage. So for after doing this, we are like pretty sure that we didn't miss any cases in our code that goes untested or something.
Yeah, cool. Thanks for adding it out. So yeah, back to the point, when code base grows, it is tough for everyone to keep context of every single function or every single thing that is being changed or being developed or being, added to code. That's where we talk about code base maintenance and developer productivity. Let's see how did this code as data help us to do it. Yeah.
Yeah, so that is this tool called Chopper that we built internally. So what that is doing is it is taking this. See, consider we have like a long repo. So what we have this functional dependency graph, right? Um, but we also know what are the tightly coupled functions, and what we will have the layers of functions that we can split across. So we were thinking to like organize our repos properly, such that okay, these related functionality should be in this particular so we can have multi cabals in a repo, right? So if it's like a big project, we want to like chop it down into multiple project and put it to its like proper functionality. We want to stick proper functions, like consider all the encryption functions, all the utility functions, we want to put it in one place. All the main domain functions, we want to put it in one place. So we use this function dependency graph for that, and we segregated the functions, and we uh, the big repo, we chopped it into like smaller pieces, which also help us in compilation time, which also help us in better understandability of the code base. Yeah.
So what Shopwood exactly does is you give it a plan and you say, I want to split into multiple couples, or you say, I want to split it into multiple modules. Then it executes it, and then it'll give you a compilable code which you can commit and push. See, this tools, see, we can also do it manually. It's not something we won't be able to do. But the thing is, once you do it, every other developer should also kind of rebase it, right? Whenever they all their features or their everything, they have to resolve conflicts and all. It takes time. So that's where Chopper comes in. We can give it out to devs and it'll be like, oh, you're rebasing it, don't rebase. just clone the latest one with your changes, and then you can simply run that particular tool with the same plan that we are giving it out. So it again rearranges for them. So there won't be any diff for them. It'll be easier for them as well. And with this, we would like to add that, okay, so let's say when teams, when there are repositories which are used across teams, right? There might be code which you don't even execute in your particular thing. But you don't want to wait for it to compile again and again and again, right? So we did a little bit of static analysis, like code analysis, saying, oh, what and all we can segregate, what and all functions, what are all components that we can decouple, and basically what it helped us is, so let's say if I want to make change, it basically cut my time very efficiently. It was more or less like, once I want to make a change, I'll just figure out where I have to make the change, and depending on that, I can estimate how much time it's going to reduce me. Like, okay, it is more or less like, you have multiple packages. Since you're using Haskell, I'll relate it with it. So we have a big repo. Even if I change the first module, you have to compile the end repo. Even if I change somewhere in the middle, it has to compile every single module after it, right? That graph. So let's say if you break that subtree into isolated components, it is more or less like only what you touch and what on top of it would compile. I don't need to start compilation from start as well. So it basically what helped us reduce on development time as well, and iteration as well, developer iteration as well.
Yeah. And about like Haskell tools, like it was already available in our community, and it was like an amazing tool. We adapted it and we wrote fewer refactorings on top of it. For example, the same use case that Ishwar was telling, for example, like some unwanted functions that we have in the code, right, which is not getting used anywhere, and we want to remove it because it adds up to some time and something. So we wrote a refactoring to get after getting the list of functions, just remove it from there. And lot of domain-based refactorings also we wrote, and lot of framework implementation we used in those kind of refactorings also we did. And when we wanted to move from one type to another type, so it's just like from you consider you move from a text to int in one particular type, and you want to like apply it everywhere. Obviously, compilation will tell us, but for a dev to go and make changes everywhere, right? It takes some time, so that running this tool, right, we'll find that pattern and it will just replace that to whatever we want. So all this kind of refactorings we wrote, and you can check it in JustBase GitHub. Our refactorings you can check, and this is the original repository link that has been pasted here. And on top of this, right, see, we know like LLMs are the future, and it's getting evolved and all of this. So we used we are like earlier, right, when we tried to generate Haskell code, the data sets was not good with LLMs, and it was not generating like most the code that we wanted it to have. Then we collected using our plugins and all, we collected the data sets, we used it to generate code, and currently we are generating Haskell code using LLM, and it seemed to be like pretty good, because we do like proper inputs we take from the data set, that whatever we used from the plugin, we give that input, we ask you to use particular functions so that it will use only those functions. And then even the output, whatever we give, it gives, right, we run GHC parser and type checker over it, so that even the output we can validate whether it can happen. So it's good that GHC is exposing all those things, so that we were able to use it, and we found we are getting deterministic output because of that. Because if something fails, we are doing a re-ask or something, all those things we are doing. And we are also able to get the functions. If LLMs are using some functions, we are also checking whether that functions is available using the function dependency graph that we have. If it's not, we are telling, no, we don't have this function, you have some similar functions, you use it, something like that. All. So that is also like very good. Yeah, we are still working on the accuracy and all, but yeah, all of these things helped us use LLMs also in a good way.
So when we started with LLMs, when we tested out saying, okay, were LLMs really good with Haskell, like code generation or let's say code suggestions, we started with very small LLMs that we wanted to fine tune and all. And then Codebase data is actually our backbone, which basically helped us, investing time in Codebase data kind of reduced a lot of time for us to build tooling on top of LLMs, make deterministic output, and then say, okay, how do you generate data sets to fine tune or pre-train? all those things. So yeah, Codebase data really helped us out to speed up with our introduction to LLMs and all, trying out LLMs. There are a couple of things we want to say why we want to continue exploring this in this particular Codebase data. So it isn't just about building tools. It is more about creating an environment where developers can do their best work. As systems grow more and more complex, these capabilities become not just helpful but essential. So there are a lot of tools that we are also trying to build. We'll be putting it in Spider repository only of JustPay. Yeah. So the major reason is more or less like we want to empower teams to make better decisions, bring them more confidence in their development, and then we also want to provide innovation. It's not only about adding code. It's also like, okay, how do you optimize this? How do you reduce that particular thing? All those things. So we want to give a shout out to GHC team because all this is kind of fascinated us when we started our journey with Haskell. It was really interesting and it's been really well structured and well written. Like you can plug and play a lot of things. Since Haskell is an expressive language, it is really good.
Yeah. So thanks. A great thanks to the GHC team.
Any queries?
So if attendees raise their hands, I can allow them to talk. If not, please put a question in the Q&A section or comment in the chat. Thank you, Chaitanya and Eswar. The fascinating conversation. It would have been nice if we had some links to your repositories as well.
We have links to repositories as well. We'll share it.
We'll share.
Here.
But yeah, best to put this up because when the video comes up, people will go back and take a look at it.
So also one more thing I want to say. So we use Neo4j community edition to basically visualize whatever things that we built, right? Like say function dependency, or let's say type dependency graphs and all. We use Neo4j extensively. Even for symbolic paths, we use Neo4j only. We used to plug it into Neo4j, and then it used to be cool for PMs to see, oh, this function, all these things can happen, and it was kind of more or less like intuitive for them. Even it's not like we don't want to keep constraints saying, oh, you can only understand how that function works if you read code, right? So it's more or less like, oh, if you have that path, it'll be just more or less like traversing. It'll be GPS for you. It'll be like, oh, I give this input, what can be the output? Yeah.